Let's talk about some of the basic properties of the convolution operation. We learned in the previous video essentially what convolution does. It's a method of combining two different signals together. In some cases, there will be no alternative other than to actually solve the convolution integral in order to get our solution. But in many cases, we can sort of do an end run around the integral and just apply a little bit of common sense and a little bit of intuition. So let's see what I mean by that. So let's start with some. Let's start with an impulse. Let's say this is my input, my system input, and that input is we'll call it input x of t. But in this case, my input x of t happens to be the delta function. Okay? And let's say, for the sake of argument, that I'm dealing with a system whose impulse response looks like, I don't know, let's just give it some arbitrary shape. Let's change it up a little bit from what we've been looking at before. Okay? So let's say this is the system's impulse response. And so my question now is, if I convolve the input signal with h of t, what am I going to get as my output? Well, in this case, I think we can just assume that we know what the answer is. Okay? And let me reason this out. If h of t is the impulse response, and the system is being stimulated with an impulse, then surely the output of the system will be exactly the same as h of t. The output of my system in this particular case has to equal whatever that shape was, is just a repeat. Okay? So, because if this is the impulse response, the system's response to an impulse, and the system is being presented with an impulse, then pretty much by definition what comes out has to be the impulse response. So look what we've just worked out here. We've just worked out that delta of t convolved with h of t is the same as h of t. Okay, because in this case the system output I got is identical h of t. Okay, so let me just draw this a little bit more cleanly. This is the symbol for convolution. We usually do like a little asterisk in a circle. So, as far as convolution is concerned, the delta function is the identity. Okay? So we know that, for example, when it comes to adding two numbers together, we know that 0 is the identity, because anything plus 0 is itself. We know that when it comes to multiplication, 1 is the identity, because multiplying anything by 1, you get that same number back. And when it comes to convolution, an impulse is the identity, because any function convolved with an impulse gets the same signal back. Any signal convolved with an impulse returns the same signal. Okay, so the impulse is the identity operator, and we can actually get a lot of mileage out of that. Let's try some other examples. Suppose my input signal now is equal to this. So let's say my input signal x of t is equal to 4 delta of t minus 3. So this impulse has an area of 4 and it's shifted to the right by 3 units. It's a pretty safe bet that my system output is going to be my very same impulse response, but shifted to the right by 3 units and 4 times bigger than it was before. I guess I never really defined how big this was before. There we go. Okay. So in this case, this is my expected output y of t. And really what I've done here is I've convolved x of t with h of t and I got y of t. Now it might seem like pretty trivial, but if we can master these basics, the more complicated stuff will feel a lot easier. Okay, let's try one more example. Suppose now that my input signal looks like this. Suppose I have an impulse at 0, and then an impulse over here at, I don't know, 3, and an impulse over here at -1, and let's make this one have a height of a half. This one have, I shouldn't say a height, I should say an area. This one has a height of an area of 1, and this has an area of 2. Okay, so let's say that's my input signal x of t. I want to convolve it with the same h of t as before. What's my output? Well, because these systems are linear and time invariant, the system's response to this impulse should be my original h of t, but shifted to the left by 1 unit and made half as big. So this will be -1, and instead of having a height of 1, this one will have a height of 1/2. And then this impulse will give me an impulse response, which is shifted by 0 and has a height of 1. And then this impulse will give me an impulse response that's shifted to the right by 3 units and has a height of 2. So this will be 3, and this has a height of 2. So once again, I've taken x of t, I've convolved it with h of t to get y of t. So when it comes to when it comes to impulses, you can think that convolving with the impulse sort of creates a copy, right? It basically creates a copy of the signal that's being convolved against it. And if that impulse is shifted or scaled, then your copy will be shifted or scaled accordingly. Okay? But we can get a lot of mileage out of convolution just by doing these shifts and scales. Last piece, let me do one that's a little bit more involved. Let's let my input signal, let's let it be an impulse at 0 and an impulse at 1, and let's say they both have area 1. Okay, so that's my x of t. And let's let my h of t look like this. Let's let my h of t, oops, let's do that in red. Let's let h of t look like, nope, that's still not red. Okay. Let's let h of t look like this. -1 to 1 with a height of 1. And that is h of t, and I wish to convolve. So, again, we're going to apply the concept of linearity. So the first thing I'm going to do is I'm going to convolve h of t with the first one of these impulses. So if I convolve h of t with that impulse, I'm just going to get a copy of h of t, right? Because we just said convolving with impulses gives you a copy. So if I convolve with the first impulse, I'm going to get that. Now if I convolve with the second impulse, I'm also going to get a copy, but shifted to the right by 1 unit. So if I draw that, here's a copy shifted to the right by 1 unit. So this will be at 0, this will be at 2. And then finally what I need to do is I need to add those two copies together. So over here I'll be adding 0 and 0. Over here I'll be adding 1 and 0. Here I'll be adding 1 and 1. Here I'll be adding 1 and 0, and then finally back to 0 and 0. So now the green signal will be my output y of t. It will represent the convolution of x and h. Okay, so y of t. Pretty straightforward. And as a parting thought, convolution has this really useful property that the order doesn't matter. So x convolve h equals exactly the same thing as h convolved with x. Okay, so x convolve h equals h convolve x. The order doesn't matter. Okay, and that's going to be super useful. We're going to be able to exploit that in some future examples to make the work a little easier for ourselves.